So should I just start now? All right, everybody. Good afternoon. It is my pleasure to introduce today's speaker, George Kiladis. So like a quick, I'll be quick here. George got his PhD from the University of Colorado. It looks from here. He has done a lot of work in tropical meteorology, and I think probably most well known for the Wheeler and Kiladis diagram, the wave number frequency diagram with the dispersion curves that you all see in the classroom and many of the classes that we take in this department. George has been, actually a quick thing, he's been a reviewer in many of my papers, so it's actually it's one of the best.
And he's still here.
So that's one of the things that I wanted to quickly note. Outside of being a great scientist, a great reviewer, always gives great feedback on things. Outside of the research has been noted. He's won the Charney Award, was in 2022. The Charney Award, and he's going to be talking today about the stratosphere and the interplay between convection, waves, and the QBO. So welcome, George.
Thanks. All right. Yeah, nice to be back here. So this talk's going to be on stratospheric Kelvin waves and their relationship to tropical convection and a quasi-biennial oscillation, or QBO. And this is work with Juliana Diaz, who many of you know, John Albers, who many of you may remember from here when he was in Madison, and also Hamid Halavan, who did his PhD with Chung Fu and Mike Wallace at University of Washington on QBO forcing. So that's going to play here. All right, motivation. Many of you are familiar with Kelvin waves. They are ubiquitous, I would say, in the tropical atmosphere and ocean. In the troposphere, they're strongly coupled to convection, and they account for a large fraction of rainfall variability in the tropics. And then in the stratosphere, there are free Kelvin waves, which are not coupled to convection. And they are known to be critical to forcing the QBO. Why do we care about the QBO? It's known to modulate the Madden-Julian oscillation, the MJO, for instance. Equatorial cloudiness, things like the NAO and so on, a very important feature of the stratosphere. And an important point is that models really still struggle to simulate the QBO, and even the equatorial waves that are responsible for forcing it, along with the gravity waves that are responsible, that aren't even fully resolved in any general circulation model. So what we're interested in here is what the dominant scales of stratospheric Kelvin waves would be, how their structures change with the background flow due to the QBO. So I'm not focusing on the forcing of the QBO in this talk. What I'm interested in here is how the background flow changes the waves themselves. What the sources of stratospheric Kelvin wave activity might be and what causes their variability, because wave activity is highly variable in the stratosphere, not just with Kelvin waves. Gravity waves are much more constant, but the large-scale forcing for the QBO, like things like Kelvin waves and mid-stratosphere gravity waves and so on, vary a lot. And then I'm going to be primarily using reanalysis products, and I'd like to show you that ERA5 is very useful for studies like this. So with regard to that last point, this is a picture from Hamid's PhD thesis, and it shows the zonal wind along the equator. So we're looking up in the stratosphere up to 35 kilometers here. And over time, several years here, and you see the descending easterlies and dash contours, westerlies and solid contours. Very regular, 28 on average month period. And what I'm also showing here in the shading is the divergence of the Eliason palm flux. So the EP flux divergence is related to the momentum forcing of the QBO. And you see some interesting features here, like during this descending westerly phase, you have a very concentrated forcing, eastward forcing shown in the red. So the westward forcing is shown in blue, eastward forcing in red, and you see that very concentrated right before you get these westerlies accelerating and then descending. And then the easterlies are much eastward, or sorry, the eastward forcing, yes, is much more diffuse. But it turns out, and Hamid was able to look at budgets of this momentum forcing, the Kelvin waves account for something like 40% of this westward forcing in these regions. So that's one main reason why we're so interested in Kelvin waves. And then another, something like 40% is due to gravity waves, both eastward and westward, because those are isotropic, and they tend to propagate in basically random directions. Okay, so as I mentioned, I'm going to use ERA5 reanalysis, and we're making use of the model level data here, which is very nice, high vertical resolution, something like 1/3 of a kilometer in the lower stratosphere. So we have 137 model levels to work with, and this data goes all the way up to 80 kilometers. So very, very useful. OLR, outgoing long-wave radiation, twice daily, 2.5 degree resolution, as a measure of convective activity, and then that's supplemented with this Klaus IR merge brightness temperature that we put together, which is much higher resolution in time and space. So this has a somewhat shorter record than the OLR, but we're going to use both for this talk. Okay, starting out with, I'm going to show a series of Hopplers. So we have OLR in this particular plot near the equator, 2.5 south, 7.5 north, for a 4-month period in 2006. So time's running up, and we're looking, along the equator from Greenwich to Greenwich here. So it's a global plot, and what you see is a lot of eastward propagation in this cloud field. And I mean, these are mostly Kelvin waves, these big features here that propagate at something like 15 meters per second. And if you look closely, you can see Kelvin waves all over the place, over Africa, over South America especially. And of course, they're dominant over the warm pool as well. So now I'm going to take that field and do a 2 to 96 day bandpass filter. So easterly anomalies are in blue, westerly anomalies in red, and this is for, I think it's this is just along the equator. So you can see these features that I mentioned propagating at 15 meters per second on the large scale. Now we're going to look at the zonal wind at 100 hectopascal. So that's right at the tropopause. The tropopause, the TTL as it's called, tropopause transition layer between the troposphere and the stratosphere. And what we see here is, again, a lot of eastward propagation. And if we look at the phase speed of many of these larger scale features, it's also around 15 meters per second. And if I toggle back, you'll see that some of these big events here seem to be directly tied to what's going on in the OLR field. So these are also Kelvin waves at the TTL. Lots of them don't make it too far, but there's a dominance, again, of eastward propagation at that level. Okay, that was 100. Now we're going to go up to 50 hectopascal. And what we see here are even more Kelvin waves. this field dominated by eastward propagation. But these features are moving a lot faster than they are at the TTL. So this one's 25, this one's 30 meters per second. And you also see an interesting contrast from the beginning to the end here. Kelvin wave activity is concentrated over the warm pool in the Indian Ocean at the beginning, and then it tends to spread out and be more circumglobal towards the end of the period. And that actually turns out to be a systematic thing that we see, because this period is a transition. It's a descending westerly shear zone of the QBO. So it actually goes from easterlies down here at the beginning to westerlies along the equator towards the end. So we think we can explain most of why this happens, where you go from activity concentrated over the warm pool to circumglobal activity. And I'll talk about that in a bit. Okay, now I'm going to show several space-time spectra. Some of you are familiar with this. Basically, this is a spectrum of OLR from 15 south to 15 north. It's a symmetric component, or like-signed component of the variability about the equator. This spectrum shows eastward power on the right, out from wave, zonal mean wave 0, all the way out to eastward wave 10, and then westward on the left. And the periods go from 96 days at the bottom up to 1¼ days at the top. So we see the familiar patterns of Kelvin waves here, westward inertial gravity waves, equatorial Rossby waves, and this is the MJO here, that big peak down at the bottom. So these are the equivalent depths for those of you who might be interested in that. But basically, the Kelvin signal, especially out here at the high end, matches, it's closer to this 15 meter per second phase speed that I showed you earlier. And it's got some dispersive-like properties to it. It's not a straight line as in a pure Kelvin wave, but that's another topic. Okay, now, same kind of spectrum, except this is for zonal wind between, again, 15 south and 15 north for the same period. This is using all the data from 1979 to 2018. So again, we see an MJO peak. This equatorial Rossby peak is missing, but we see a westward inertial gravity and Kelvin peaks as well. And if I toggle back and forth, you can see that a large portion of these signal overlap between the zonal wind at 100 and the OLR measure of convection. So there's some relationship there. Okay, same exact thing, except this is 50 hectopascal. So now we're in the lower stratosphere. And if I show you, again, 100, you still see a Kelvin peak here. The MJO is missing, that we saw at the other spectra. And the westward inertial gravity wave is also there, but these are associated with higher equivalent depths. In other words, these waves are moving faster at 50 than the ones move at 100, for instance. And then we also see these external Rossby mode peaks. This is the so-called 5-day wave here. I won't be talking about those, but that's also another very interesting topic, and something that, as you'll see, is also affected by the QBO, turns out. Okay, so everything I just showed you was based on the entire sampling period, 79 to 2018. So now what we're going to do is we're going to condition spectra on the QBO. And the way we do this is we take a plus or minus 1 standard deviation of the zonal mean zonal wind, in other words, a QBO index, And we split that into two samples. If it's beyond +1, it's QBO westerly sample, and if it's beyond -1, QBO easterly. So we have 109 months in this sample of westerlies, and the mean flow is almost 11 meters per second from 5 south to 5 north for that sample. And in the easterly phase, the mean flow is -17 meters per second, so almost a 27 meter per second change in the zonal mean flow just between these two phases of the QBO, and roughly equal sample sizes for each. Okay, and here's a picture of the zonal wind at 50 for those samples. This is for QBO easterlies, so easterlies is shown in blue here. You see this wide region of easterly flow along the equator during QBO easterly, and then during QBO westerly, a much more confined equatorial westerly perturbation with really tremendous meridional shear involved, especially in this westerly phase here. Okay, is there a question? By the way, please feel free to interrupt if something's not clear. Hi, Matt. Okay, so that's the plan view at 50, and this is a vertical section going just now from 20 south to 20 north for the westerly phase. So you see this really strongly confined westerly perturbation with, again, tremendous vertical shear, in this case, from westerlies to easterlies as you go up. And this is for the easterly phase. We have a much wider region, as I showed in the map, of easterlies during that phase, with this westerly QBO phase above it. So this is all based on 50 here. Okay, here's the spectrum for zonal wind at 50 using all data. And the implied phase speed of wave 1 Kelvin wave, for instance, is 31 meters per second, just like we saw in that Hofmüller. So now we're going to look at the westerly QBO spectrum. So here's all the data. Here's westerly. And one thing you see is that the phase speed in westerlies is faster. But the difference here, by the way, is from 31 meters per second to 34 meters per second. So only a 3 meter per second difference there. And you see that the signal's a bit narrower than when you use all the data for the westerly phase. And then if you look at the easterly phase, you have a much broader band spectral signal. And all of a sudden these external Rossby modes show up much more strongly in the easterly phase as well. So that's the difference. 24 meter per second implied phase speed here, 34 meter per second here. So a 10 meter per second difference in the phase speed of the wave, even though the background flow has an almost 30 meter per second difference. So that says something more about the source of the wave.
Yeah, George, is the geometry of those two bands on the horizontal map at play here? I mean, in other words, the westerly strip has cyclonic vorticity on both sides of it, traps waves. Is that something that's going on?
Yeah, definitely.
Oh, okay.
Yeah, so that helps, certainly helps the trapping.
Yeah.
Yeah, yeah. So that's an important factor that's going to come up again later in the talk. Okay, so big differences, and we're really interested in how the flow affects the structure, first of all, of these Kelvin waves, and maybe even their source regions. So what we're going to do now is we're going to filter for Kelvin waves using zonal wind. We've done this a lot for OLR, where we take a box and we just do a Fourier transform, zero out all the coefficients outside a particular box, and we end up with a filtered data set for Kelvin waves. And we're using, we're going to try to be as objective as possible here. We're using a very broad filter, which actually brackets almost all the Kelvin activity that you can see in the entire stratosphere, as well as the OLR signal too. So we're just going to use the same filter for everything. Eastward only 2 to 25 days is the filter. And by the way, as you go up in the stratosphere, if I showed you 30 or 20 or 1 hectopascal, these Kelvin waves just keep getting faster and faster. They go to higher and higher equivalent depths, and that's primarily due to damping. I won't have time to talk about that in any detail, but yeah, pretty interesting once you start looking in the vertical at the behavior of these waves. Okay, so now what we're going to do is we're going to use the same filter I just showed you and filter OLR. So we're going to look at the convectively coupled Kelvin waves in the troposphere. That's the basis. And we're going to regress OLR and zonal wind at all levels against time series. In this case, what I'm going to show you is a time series of Kelvin filtered OLR in the Indian Ocean on the equator in 90 east. So we just have a time series of OLR and we regress the entire global fields of anything we want against that, just to see what's associated with it. So we have 3 samples. I'll show you in this talk just the QBO westerly and QBO easterly results, the 2 extremes. Okay, so we can produce pictures like this. This is a picture of the zonal wind along the equator. So westerlies are in red or orange, easterlies in blue. And this is, so yeah, we're just along the equator, and I'm only going from Greenwich to the dateline here in this particular plot. And we have a corresponding picture of the OLR signal. So I'm plotting this for a -1 standard deviation in the Kelvin filtered OLR. So this negative signal here represents the convective region. So we have convection here, and what you see is that we have in the troposphere low-level convergence, actually westerlies kind of extending into the convective region itself, upper-level tropospheric divergence. So there's the mass circulation associated with the convection. And then we have easterlies at the tropopause above that. Then we have westerlies above that, easterlies, so this layered structure, which is a response to this eastward moving convective signal. Because this thing will be moving eastward. It's a convectively coupled Kelvin wave. And if I show you a lag regression, there's day -2, so the OLR minimum is back here at 80 east in this picture. And as we move along, we can see this whole pattern moves eastward along with this OLR signal. In other words, this is a forced response to convectively coupled Kelvin wave convection.
Clarification, Lester?
Yep.
So when you started this section, you talked about using 90 degrees east OLR as the filter, but you're actually doing it at various different longitudes?
Yes, no, these are time lags. Sorry, I didn't make that.
So it's still all at...
Yeah, so this is the simultaneous relationship at day 0. Okay, so we have the minimum here, and then it's just taking all these fields a day later and seeing how they evolve in time.
But it is associated with a propagating convection region.
It is. As you see the OLR moves east, it weakens, sampling and everything else will cause the signal to weaken. But, okay, so I'll just show you. Okay, so that's 4 days after, backing up to day 0. So in 4 days, that's what happens. The whole thing shifts eastward. And then by day 10, what you see is a lot of signal, not much left down here, but a lot of signal up here in the middle to upper stratosphere. We're going up to 1 hectopascal. We're going up to 50 kilometer height here. So here's the tropopause again, 100. Troposphere, and then this is all stratosphere signal up there. And yeah, maybe this will make it a little clearer. Basically, it's Hofmuller of what I just showed you. The zonal wind and Kelvin filtered OLR over time. So along the equator at day 0, it's at 90 east here. So basically, in the shading is the OLR. So that's moving eastward by design, really. I mean, we filtered for Kelvin, filtered OLR, so it has to move eastward. But we've shown in plenty of studies that that's a realistic way to look at it. And you can see at 100, so this picture is for the zonal wind at 100 in contours. So you see easterlies, just like we saw in the vertical section. And basically, the pattern, the idea is that the pattern is being dragged along by the heating. So it's a forced response. That's why we call it a forced response. And then you have suppressed phase after, so time's going up, right? So here, you have convective activity, then it's suppressed. And then there's a suppressed opposite sign response after that. And that's moving at about 15 meters per second, just like we saw in the Hofmullers of OLR. Okay, so that's the day 0 picture again for QBO westerly. Wait, sorry, what was I showing? I was showing QBO easterly, sorry. Okay, so that's the day 0 picture now for QBO westerly. And similar sort of thing, exactly the same approach, except it's for this QBO westerly sample. Minimum in OLR here, there's where the convection is. And we see, again, easterlies at 100 above where the convection is. But, did I put it in here? Okay. I'm going to go back to day 0 here. There's a huge difference between these plots. You see the much larger vertical wavelength and a more tilted pattern here in QBO easterly than you see in QBO westerly. So if we look at the evolution here, what's going on, again, the Kelvin OLR signal is moving eastward. And in fact, if you look closely and compare what's going on in the troposphere in these two samples, they're not much different from each other, but the stratosphere signal is way different. In fact, you have very little signal making it up above those westerlies at 50. And if I show you day 10 here now, we don't have much signal up here. And if you compare that with the easterly result, you can see that the signal in easterlies propagates very readily vertically up into the middle and upper stratosphere. So basically, these waves are encountering a critical level where their phase speed matches the background flow speed in westerlies, and they're getting absorbed, and they're giving up their momentum to the QBO. You know, that's, I mean, nothing new really. It's been known that that must happen, and that's how the QBO is forced. But you know, now we're in a position to actually look at what goes on at these critical layers and how this background flow changes the structure of the waves themselves. So all of this so far can be explained by relatively simple linear theory. It's pretty amazing, actually. This is a diagram straight out of Holton's textbook of the vertical structure of a Kelvin wave. So the phase, okay, as we saw, I guess I didn't point it out, but let's just back up real quick. Phase goes down if you watch what's going on here. It's even more evident in the easterlies, but these waves are moving downward over time. So that's what this arrow represents here. So downward phase propagation, and then the group velocity is upward and eastward, so perpendicular to the phase lines here. And then you can measure a vertical wavelength. This is just a half wavelength here in the vertical, and then of course our horizontal wavelength. And it turns out that the tilt that you see is related to the vertical and horizontal wavelengths by this simple relationship down here. So if you have larger vertical wavelengths, the waves tend to be more tilted from the horizontal. Okay, and you can quantify that. So the vertical wavelength in linear theory should go as the intrinsic phase speed divided by n with a 2 pi factor. So this is called the intrinsic phase speed, or the phase speed with respect to the background flow, or the phase speed you would see if you were moving with the background flow. So there's a straight linear relationship between that and that vertical wavelength. So we can actually plug some numbers in here from those regressions I showed you. And so we get, for the westerly phase, using that 10.8 meter per second U-bar, we get a vertical wavelength of 1.2 kilometers versus, for the easterly phase, 9 kilometers. So something like almost a factor of 7 difference in the vertical wavelength, which actually, I won't go back, but is actually what you see in those regressions. So that works out pretty nicely. So basically, for a given background flow, Kelvin waves in easterlies should have a larger vertical wavelength than in westerlies. And then as the wave phase speed approaches the background wind, the vertical wavelength should go to 0. And that's where the absorption of the momentum takes place at that critical layer. So that's how the forcing of the Kelvin wave works for forcing the westerly. And then the vertical group velocity is much more sensitive to the intrinsic phase speed by this quadratic factor. And if you plug numbers for those, and okay, so what this relationship says that for a given zonal wave number and phase speed, that Kelvin waves in the easterlies will have a faster vertical group velocity. In other words, they'll propagate upwards much more quickly, which is exactly what we saw in those easterly phases in the Hofmüllers. I'll get back to that in a minute. And then, likewise, the upward group velocity approaches 0 when the phase speed of the wave approaches the background flow. And again, that's what happens at the critical layer. And then, just as an aside, I mentioned damping earlier, and radiative damping is inversely proportional to the vertical group velocity. So basically, the slower the group velocity is in the vertical, the more time there is for radiative damping to dampen the waves. And that's scale dependent by this wave number factor. So it turns out that the damping is much greater for smaller wave number. Okay, this is the Hofmüller I showed you for this forced response at the TTL. We had this 15 meter per second convective signal just forcing this response and dragging it along. Now, if we look at 50 at this, so the basis again is this Kelvin filtered OLR at 0.90 here. If we regress now the 50 hectopascal zonal wind against that, this is what we get. So this is moving 15 meters per second. At the same time, at 50 above, you get a much faster Kelvin wave. So in other words, that force response launches these faster Kelvin waves further up in the stratosphere. And this one's moving at that typical sort of phase speed we saw in the Hobmullers at the beginning, 31 meters per second. In other words, the slower portions of the force response are filtered out, both by radiative damping and, it turns out, by the changes in the zonal wind that you see between those two levels. So what about these stratospheric Kelvin waves? Now we want to look at the structure of these faster waves further up in the stratosphere. So to do that, we're going to do an EOF analysis. It's just a standard covariance matrix EOF of Kelvin filtered 50 equatorial zonal wind. So we're taking the zonal wind only along the equator. That's the basis. So we take the zonal wind from, all the way around, Greenwich to Greenwich. We filter that for Kelvin, for the Kelvin wave in that box that I showed you earlier. So same sort of approach that we did for the OLR. And then we get EOFs. And it turns out when you do this for propagating fields, you tend to get EOF pairs. So you get an EOF 1 and an EOF 2, and they're in quadrature in time and space at lag 0, but at positive or negative lags, they're actually correlated, highly correlated, it turns out. In this case, something like 0.9. So they form a pair representing a propagating pattern. And you can calculate statistical significance, and in the plots I'm going to show, anywhere you see a wind vector, it's statistically significant. And then, again, we're going to condition these EOFs on the face of the QBO like we did before. Okay, so here's the first EOF. Again, the EOF itself is only the zonal wind on the equator. This is for the westerly sample, and I'm taking the zonal and meridional wind shown as vectors, and then the geopotential shown in shading. So orange is positive, blue's negative perturbation. And I'm just projecting those fields onto that EOF. And here's the leading mode. And what you see is high geopotential height in one hemisphere, and then opposite sign in the other hemisphere. So it's a wave 1 pattern that comes out first. And then the zonal wind is primarily zonal wind down here, which is just what you'd expect for a Kelvin wave. Here's the theoretical pattern. So zonal wind in phase with geopotential, and then decaying away from the equator. So the max is on the equator. It's exactly what you see. So there's no doubt we have a Kelvin wave isolated here. And then, as I mentioned, if you do this, you get the pairs. So you have 1 and 2, you can see they're 90 degrees out of phase with each other. And then again, they're highly correlated in time. So you have a pair that describes that zonal wave number 1 Kelvin wave. And then the other nice thing, okay, so yeah, the correlation is 0.83 between these principal components. Then the other nice thing when you get that is you can square those two PCs, sum them, take the square root, and you get an activity index, just like you would for OMI or RMM for the MJO. So that's another really nice feature. So we can actually look at how Kelvin wave activity changes. And then, oh, I didn't put the pictures in, but so EOF 3 and 4 are wave 2 Kelvin waves. EOFs 5 and 6 are wave 3 Kelvin waves, and so on. So this approach works pretty nicely in this particular case. Doesn't always work out like that, but I think it's a really nice objective way to isolate these disturbances. And then again, like we did before, you can do the lag regression and watch the evolution. Also, I have to mention, there are extratropical signals associated with these Kelvin waves, and it really pays to split these into seasons and look at that in more detail. Something that we're going to do down the line. So these waves are not completely isolated from the extratropics either. Okay, so yeah, you can play those kinds of games and look at how the waves evolve. Okay, so this was all for the westerly phase. Same exact thing for the easterly phase. So we see, again, a Kelvin wave, but if you look at the structure compared to the westerly phase, all of a sudden you have a much wider Kelvin wave, and it's actually not a pure wave 1 signal either. It's more confined out here over the Indian sector and the warm pool. So that difference in latitudinal extent can also be explained easily by linear theory. This is how you would calculate the equatorial radius of deformation. In other words, it's the e-folding distance of a disturbance that's trapped on the equator. Again, the intrinsic phase speed comes into play over beta, or the meridional gradient, the Coriolis parameter. So basically, what this says is that for a given phase speed, if you have Kelvin waves in easterlies, they should have a larger meridional width in westerlies. And again, you can quantify this, and if I just plug in the numbers from the regressions, during QBO westerly, the Kelvin wave moves 34 meters per second. There's the background wind. You get 12 degrees versus QBO easterly, 17 degrees. So there's a 5-degree difference, and that's actually just a half width. So that's just the difference on one side of the equator. So it comes down to a 10-degree difference in the width between westerlies and easterlies. And by the way, this would also have implications for the forcing of the QBO too, right? You have a much wider Kelvin wave propagating vertically, so the forcing region is that much wider too, which may at least partially explain why the QBO easterlies have a much wider extent than the QBO westerlies. And again, Hamid was able to infer that as well from his budget analysis.
Is it fair to say, George, that at least in the southern hemisphere, the difference between QBO westerly and easterly is reflected in a less wavy flow in the easterly?
Yeah,
phase?
right, look at that.
I mean, the mid-latitudes are fundamentally different.
Yeah, yeah. I don't know.
Does it decay away? I mean, does the signal actually mean as much far down in the low latitudes? Or,
I mean, that's, okay, well, for one thing, this is a statistically significant signal.
Wow.
All the way down to Antarctica. And in this case, even though you have high amplitude here, the correlations must be too small.
Yeah.
So, there's probably a lot more noise in this picture down here. And certainly up here, you don't have anything either.
But even so, the waves in the westerly phase are not so noisy. They're substantial, right?
Yeah.
That looks like a big difference.
The other thing is that you have westerlies here, so you're actually allowing wave energy to propagate in laterally from the extratropics as well.
Yeah.
So there may actually be some sort of two-way interaction
Very cool.
going on. Yeah, we're really, really interested in
Yeah.
this part.
So,
Yeah.
Since northern hemisphere sudden warmings occur preferentially during easterlies, and you have a broader meridianal scale, is there any notion or evidence that there could be some influence of more of an effect of Kelvin that's somehow being involved in that?
Yeah, I think so. I mean, you know, Holton tan effect probably is related to what's going on here. I mean, for this particular Kelvin scale, we don't see a signal, but yeah, maybe. Really, really interesting stuff, and yeah, we need to talk. Okay, let's see how we doing on time. All right. Okay, so we've got these EOFs, right? I'm going to just show you quickly what the vertical structure of these free modes. We call them free modes because they're not coupled to convection. So the basis, again, is the Kelvin wave at 50 based on the zonal wind. John. And so I'm looking at the vertical structure during QBO westerlies and QBO easterlies for those two samples I showed you earlier. And you see the same thing we saw earlier. In QBO westerlies, much narrower, smaller vertical wavelength and a much less tilted structure as opposed to QBO easterlies. And you can see here, this signal is propagated much further upward in QBO easterlies compared to QBO westerlies, which I think accounts for the fact that in that Hobmuller I showed at the beginning, during the easterlies, the Kelvin wave activity is more confined to this eastern hemisphere than it is during QBO westerlies. And this also, by the way, does say something, it must say something about the source region for these waves too. They're not out here, they're back here. And ray tracing arguments in previous studies suggested that convection over the warm pool actually propagates Kelvin wave energy upward and eastward all the way around until it reaches the stratosphere once it comes around completely in the eastern hemisphere. But that's, again, another topic. Okay, just quickly, I want to mention a little bit about the variability of Kelvin waves. So as we saw, we can come up with an activity index. We're taking monthly averages of this for the wave number 1 Kelvin wave, so PC1 and PC2. We're constructing monthly averages of that activity. And then we're essentially calculating a z-score. So we're normalizing that activity by its seasonal cycle. Okay, so this is what the 50 hectopascal Kelvin activity looks like on a monthly basis, going all the way back to 1979. And you can see there is something going on here that seems pretty suggestive. If I superimpose the QBO, again, we normalize that. So that's based on the 5 south to 5 north index that I described earlier. You can see that there's a pretty strong relationship between the QBO and this Kelvin activity at 50. It's 0.42, which is pretty good, but still most of the variance in this Kelvin activity is not explained by the QBO. This isn't too surprising because, as we saw, the Kelvin waves will be absorbed in a descending westerly phase of the QBO. So naturally, at that level, there's going to be a pretty good correspondence there. Now we'll drop down to 70, and all of a sudden, we have all this Kelvin activity going on, but only a 0.14 relationship to the QBO. And the QBO still exists. You can see it in the red here at this level. It becomes weaker and weaker as you get down to the TTL. But it's still there. But there's all this activity, all this variability in Kelvin activity.
Are you defining that Kelvin wave activity using some sort of a runny mean or like a
Yeah, this is just, these are just monthlies for now, just because that was the simplest thing to do. We just got started on this, so.
It's not like an envelope variance or something like that.
Yeah, I mean, yeah, we could certainly get more sophisticated in the way we're doing this. So we're thinking about windowing and how we should do that to capture the, maximize.
Wavelet analysis.
Wavelets would be good too. Yeah, that would be, yeah, really objective. So this is less objective, but I think still gets the point across. Here's 100. Lots and lots of Kelvin activity, Kelvin wave variability, much of which, as we saw, should be related to the tropospheric convectively coupled Kelvin waves. But the correlation here is only 0.08, so basically 0. And you know, this is it's interesting. It's kind of handy though that we can't use the QBO. There still is some QBO here, but it's very weak. But it's kind of like ENSO when you're doing analyses a lot of times. If you're not interested in ENSO, you got to deal with it and, you know, get rid of it. So, you know, here we don't have to worry about the QBO so much. But actually, to be honest, at 100, you do have to worry about ENSO when you're talking about the zonal mean zonal wind. So this activity may be more related to ENSO, but I looked at that briefly, and I haven't seen anything there yet. So these Kelvin waves should be excited by convection, and this goes back to a classic paper by Salvi and Garcia, 1987. And they showed basically, in a nutshell, even just white noise heating in the troposphere can kick off equatorial normal modes, Matsuno's modes in the stratosphere. They're normal modes. The atmosphere wants to oscillate in those modes, and it doesn't take much, apparently, to kick them off. So you don't even need forced Kelvin waves to force, you don't even need tropospheric Kelvin waves to force stratospheric Kelvin waves, in other words. So we want to look at this variability and the source of this Kelvin wave variability. So again, we take our index, and now we're just going to condition, instead of on the QBO, on the Kelvin activity, the wave 1 Kelvin activity that we get from those pairs of PCs from QBO, or yeah, from the pairs of PCs that we get. Actually, in this case, I'm using the entire data set to generate the PCs. And then we're just going to condition space-time spectra on times when you had beyond 1 standard deviation activity above, and then -1 standard deviation activity below. Okay, so I'll be quick here. Here's the first result for 100 Kelvin activity. So I've taken the spectrum, the OLR spectrum for active Kelvin wave months minus the spectrum for the inactive Kelvin wave months. And you can see this seems to be working, right? We actually have a signal down here in the OLR, which is reflective of those convectively coupled Kelvin waves that I showed you earlier. And then not much going on at other scales, although even wave 2 Kelvin waves in the troposphere can apparently influence wave 1 Kelvin wave activity at the TTL. Now, I mentioned earlier, I'm also using the Klaus spectrum, Klaus data, which has much higher spatial and temporal resolution. So here we can go out to 6 hours, down to 96 days. And this is out to waves -72 to +72. And you see something pretty interesting here. I'm only shading the positive differences. So once we get out away from this Kelvin region down here, we see something pretty interesting. There seems to be more eastward convective activity going all the way up into these gravity wave scales when eastward Kelvin waves at 100 are more active. If we do the same thing for 70, that's the result for OLR, that's the result for Klaus. So those look pretty similar. The only difference is no, that's wrong. It's 83 to 2018 versus 79 to 2018 for OLR. So these are showing more or less the same kind of results. We see a similar sort of signal, not quite as strong, more activity on the eastward side when wave 1 Kelvin waves are active, and the same thing for 50 out here as well. So some indication that eastward propagating convection, even if it's not of the scale of the Kelvin wave itself down here, can kick off Kelvin activity in the stratosphere. I have to say I'm a little bit worried about this result so far. We just got going on this, that there may be some aliasing going on with things like the seasonal cycle. We're going to have to look more carefully into that. And then also look at the impact of ENSO as well. Okay, so here's the summary. I won't go through this, but if we're running out of time, but you can read that and hopefully time for a question or two. Thank you.
So you showed that ER5 has the vertical resolution in the stratosphere to capture the QBO. But there's a lot of people that argue that because of the gap in observations in the tropics, the actual predictability or the analysis of the convection is not very well constrained. If you found, that the behavior of the ER5, OLR in the tropics is reasonable, or is it this response in the stratosphere to kind of white noise?
Yeah, so the OLR itself is a satellite product as well as the Klaus. So
Okay.
that's a separate, but we have done a lot of comparisons between ERA5 rainfall and OLR, and it gets some of it, not perfect. We just had a discussion about that earlier, but in the stratosphere, there's been a lot of work from satellite data looking at Kelvin waves in the zone and using various, lots of different satellite data sets. And some of that stuff is very high vertical resolution, doesn't have great horizontal resolution or coverage, but I think they have pretty much seen most of these signals that I've talked about here. Actually, much of what I showed, probably most of what I showed, except for maybe the force response, is not really new. We're trying to quantify it a bit more, but the ERA5, it gets trillions of satellite observations assimilated into it at each cycle. It's just amazing, and whether it's handled properly or not is another issue, but it's amazingly good at the large scale stuff, and the horizontal for sure. The vertical less so, but you do have things like satellite occultation data that go in, and those are really excellent vertically resolved temperature. So you give the assimilation system temperature, and it can handle it. It produces winds and does a pretty decent job. So yeah, we trust everything I talked about here. We trust they're large-scale signals. Right. Even some of that narrow vertical structure, I think, is spot on. You wouldn't trust the exact numbers that come out, but once you do these kinds of statistics, I mean, we're throwing in the entire data set. Yeah. So for an individual event, maybe not, but for these statistics, I think it's okay. Thanks for bringing that up.
For your EOF analysis and the wave activity metric that you're calculating, if you were trying to isolate these equatorial Kelvin waves, it does look like there's a lot of variability that's happening at the high latitudes that might be related to the Kelvin waves, but simply not the Kelvin wave. For your activity index, would it make sense to either like have a cutoff, a meridional cutoff, or some sort of difference where you're trying to maximize variance, but you have a die-off as you go to higher latitudes, and then you might...
Yeah, well, don't forget the activity index itself is just based on the equatorial zonal wind.
Okay.
So, you know, we're not, so that stuff that shows up that's
You're
just,
putting that up for the
just
index.
what it is in the data at
Yeah.
least, which again, I mean, those are huge, large-scale signals, so they're for real. Whether, you know, there's a systematic relationship between what's going on in the extratropics and whether that's forcing Kelvin activity at times, or vice versa, or there's a two-way thing, we don't know yet. But I think in one of the first plots I showed from Hamid's thesis, there was a disruption in the QBO that took place, I think it was 2017. Yeah. And that's been blamed on mixed philosophy gravity waves actually propagating in from the extratropics and other wave activity as well. So yeah, there's definitely, and again, when you have westerlies on the equator, you can get lateral energy propagation into low latitudes from the extratropics. So that's certainly going on. And I thought we'd see more evidence of that. So far, it's a bit elusive, so we're going to have to do some more work.
And a second question about those EOFs. For the higher EOFs, you said that you could see paired waves for the higher wave numbers. Do you see a similar higher wave number pairing in the mid-latitudes as well, or like?
No, you still see the large-scale stuff like wave 1, 2 dominated stuff for those higher modes. I have pictures with me if you're interested. We could look at. The EOFs themselves, of the Kelvin waves themselves, are almost pure wave 2, almost pure wave 3 in QBO westerlies. And then again, they're more confined on the eastern side in easterlies, just like you saw for wave 1. So that seems to be working out too. But yeah, the extratropics, yeah, that's a whole another area that we have to check out.
Along those lines, George, and this probably is naive, I don't know this field well at all, but is there a connection between QBO easterlies and southern hemisphere cold season ozone spikes?
Ooh.
Or maybe westerlies and cold season ozone spikes? Because it seems, the idea that I have in my mind is the easterlies have those big waves, which
Yeah.
probably expands the polar vortex. We're looking at 50 millibars.
Right.
And so that's going to be harder to really get your chemistry going, pre-Montreal Protocol anyway. And maybe there'd be a big difference in the off years, if that's phased at the right time.
I think that would come down to what this Holton-Tan effect and how the QBO impacts the high latitudes, which it does.
Yeah.
So yeah, I'm not sure about the ozone part. There's certainly ozone. Maybe Andrea knows more about this than I do.
Yeah.
There's certainly ozone.
I'm off the top of my head, I know northern hemisphere, but the southern hemisphere is a good question.
Yeah, anyway.
But
Thanks.
certainly, you need a stable vortex.
Yeah, and
So if you have more wave 2 activity in the southern hemisphere, I would expect less ozone.
Yeah, that's what I was thinking. Okay.
And it's at that, you know, the actual depletion occurs pretty low.
Yeah, yeah. So.
Mhm.
I would probably think it's more about the timing of the breakup, because the southern hemisphere vortex is just so strong that it doesn't really break up, so it's probably going to impact the seasonality of the final warming as opposed to in the winter.
But then your waves would do some of the breakup work anyway, right?
Yeah, eventually, yeah. Yeah.
So that they help in that regard, but they may not be the whole thing.
good topic for future
Yeah, yeah.
research.
Last questions? All right, if we don't have any more questions, thanks, George, for coming.